is that is we are going to retain the whatever the initial condition, that is the initial transfer parameters and time moments. So that means transient response as well as the statistics we are going to retain here after addition of the from higher order to lower order. That is the objective. Next coming to the need of the method. So that is what is the actual need to see the data. So under one, that is the next one is the description of the our proposed method. So here the description is basically the method is should be comparing with the other method. So whatever the previous existing method, so what are the drawbacks of those methods, that will be compared with the our proposed method, and what are the drawbacks present in the previous method will be overcome how we are going to overcome this method, we are describing this method, and coming to the application of results. So application results means here we are going to test our method with a 4 numerical examples. I have taken the 4 examples here. So those methods, the 4 methods will be done by this all the methods that we are having the Luca, Gutman, Lusty method and our proposed method. So that is from the comparison, you can easily understand what is the improved outcome of the response. So they are finding the step response here. So that will be compared with the other methods or the existing method, and what is the improvement of that we will see in the application results and features of conduct phase. So that is the now up to now this method is applicable for the only for the linear time unit system, not for the other method. So that I am trying to guide and myself is trying to improve the invariant, not variant system, and also parametric oriented. So that is the feature one. So next coming to the objective. So this is the object of the method, proposed method. That is to develop a method, new method. That is from to reduce the higher order system, that is linear time system, and reduce the lower order. So while reducing the convey with differentiation technique, at the same time we are retaining the, so we are taking the higher order system to the same one. So that will be after reduction, that is also retain the same state, and also we are maintaining the time parameters and initial marker parameters of the retain same axis. That is the advantage of this method. Next coming to the need. The first one is the need modeling. So modeling here, that is we are modeling the higher order system. So suppose you take the design of the higher order system, so it is very complicated. So because of the order system increases, so the number of components and design system is very complicated. So that we go for the real-time application will be complicated. So that will be reduced to the lower order. So then that will be, so that means after getting the lower order, so whatever the response we are getting in higher order, that will be same or improved from the reduced order. So that is the modeling here. Order reduction of the same. And coming to the stable reduced order model from the same original system. So that means after addition of the system from the higher order system to lower order, so that system will be stable. So the reduced to lower order. Suppose you take the 8th order or 10th order system, that will be reduced to 2nd order system. It will be easy to implement that. Because of the number of components will be very less, so automatically we can easily design or implement the system. So that is the next one. Next one is here the main advantage of this method is here maintaining the transient as well as the steady system will be safe. So while you compare with the original system, you find what is the transient response, but the steady state will be same as the after addition of the second order, the lower order system, this will be same. That is the main advantage of this one. Next coming to the overcome limitations of the previous existing methods. That means to take the pattern or Lucas or Gutman methods, those will be some of the drawbacks. Suppose you take the example which is needed while taking your application results, you can compare the what is the drawback, how we are going to overcome the drawbacks and Lucas by this method. Next one is the distinction method. So here we take any system that will be described or analyzed by using the transfer function model. So that is here the original system transfer function is given by the first equation. So that is in terms of the equation of the transfer function, So we can for that one, by using the quotient of the original transfer function real transfer, and we return to second order. So after this case, this is the reduced model, and first one equation is the original system model. So after reduction of system from the higher order to lower order, we can get this architecture with the quotient of the V and so on. Let us get the after reduction of the system to the lower order, we will get some quotient that will be reduced model. Next coming to the, so here we are describing the method. So originally we are having original system with the transfer function model, that is have the numerator and denominator. So initially we are reducing the denominator factor to the lower order. So with help of this generalized equation that we are finding the quotient first. With help of the quotient we are developing the denominator. As well as we are saying reducing the numerator of the original system to the lower order of the original system. So this is of the denominator reduction term. How we are doing? So that is we are here. We are using the technique which is called the differentiation technique. So this is a generalized reduction process of the denominator factor. So that is DKF this one. So here we are finding the differentiation technique, nothing but we are finding the factorial of this one. So here the factorial will be finding this one. DKF will be P factorial by Q factorial by P minus P factorial. This is after finding the application of the several denominator factors. So generalized equation will be given like this our method. So the DKF will be equal to K plus 1. So that is the K equals here the order of system. If I say original system order will be higher order, that might be 10 order and 100 order. That will be reduced to define our system that we K will be reduced order model and K will be 1 or 2. Generally here in this method we are reducing the second order system. So then only it will be easy to implement. Next coming to the how we are going to reduce the numerator. So here also we are finding the retaining the original parameters, that is the time moment and initial master parameters. So that is the K, and the K equal to G plus M indicates the P is the time moment parameter and M is the initial master parameter. So here we are partitioning this is the entire numerator into two parts. So that is the T1 to P power Kn, so this one is the first part and second one is the master parameter. So that is we are participating the entire numerator from higher order system to the lower order system of these two participations. That is the first part indicates the moment time on parameter and second part we are indicating the initial master parameter. So that means we are retaining the time moment and initial master parameter same as the original system even though its reduction process is there. So that is the advantage of this method. So here the quotient Cg and the mm. So it is the time moment parameter and initial master parameter will be calculated by this equation. This is after analyzing the equation finally we are generalizing for the any system to get the time moment parameters and the initial master parameters. So then coming to the application results. Here after reduction of the description of method, there is this proposed method. We are apply this method to the taking the numerical example. So this is first numerical example application result. So here the first one indicates a original system. So which is hand the order of the fourth order. So that is the denominator factor indicates the order of the system. So that is the S14 indicates the order of the system. So n equal here 4 and that will be reduced to second order system. So actually our original system is a fourth order system, that will be reduced to second order system which is of this one. Already it is discussed in the previous how we are going to reduce the denominator polynomial, that is the beta of L. So it will be given to this after getting the S. So here we are finding reduction of this means we are finding the factorial of this one. So here NC indicates the N here, that is the original system order, that is fourth order system, and getting the present beta of L. And finally by taking the second order system numerator direction, that is the LTI System getting this one. So this is the after of indicates this proposed the after reduction of our proposed method is this one transfer function model, and the after is indicates the original system transfer function model. So after that, the application will be the MATLAB. We have implemented with the MATLAB. That is we are finding step response here. So you see here, this is the red step response indicates the color. The color which is in red indicates the original step response. And coming to this, so the green will indicate the step response which is proposed by our method. So you see here the step response of original system compared with our proposed method, the transient as well as the steady response will improve. So that means the transient response is priced out as possible compared to original system. So that is the improvement or advantage of our method. And coming to the second advantage of this one, so by taking a look at good plan, here the difference between the order of the numerator and denominator of the unique answer function should be one only. So if it is more than one, so it is unable to find the apply the low cost method. Whereas coming to our proposed method, we can implement whatever it may be written. It may be 1 or 2 or whatever it may be, we can easily get the improved version of the step response here. So that is the main advantage of our method. So in the original system, so after that one, so the entire indicates the original system of response and green color indicates the residual model step response. So the transient is dies as early as possible compared to original system. This is a second numerical example. So here also, finally, step response of the B method, that is the good point method. So here the difference only between the numerator coming with transfer function. This is the difference between the residual model. Numerator and denominator, they have the difference only one method. So you can also apply the good point method. So whereas coming to it is more than one, not possible. So that is the drawback of good point. That drawback is also overcome by this our method. So this is our example. Here also same we have the difference between the original system. Difference between the numerator and denominator, we have only single method. You can apply all the methods. So that is we are taking the response here also again as improved version of it. So green color indicates or the step response of the proposed method. So that is the response will be greater as possible to the steady state, and also the transient will be. So same as whatever the sum they will get, you look at and look at a cardiac transmission method. Here the original system is a stable one. It is stable. Now tradition of those methods, raising the required and refined method, that will be fails unstable. So that the system will become unstable some cases. So whereas coming to the by method, our method will be always stable. System will be original system will be stable. So this is our application oriented result, improved version result. Next coming to the feature. So after our method is limited to only linear time variation system, not for the variant or other method, other variant system. So that we are trying to improve that linear variant system also, and also we are trying to apply the dimensional variant. So if it is a system is described by the differential equation, you can easily analyze by this method, and also you have to find out the response. Instead of higher order system to be lower order. So non-linear system also applying the time. And coming to the conclusion. So it is method. So the main advantage of this method is, even though our prediction higher order to lower order, we are retaining the time moment and the markup parameters to the original system. So whatever the time moment and the initial markup parameters will be there, that will be retained in the residual model also. So that is the system conclusion. Thank you. That is, we are going to retain the whatever the initial condition, that is the initial markup parameters and time moment. So that means transient response as well as the steady state. They are going to retain here after addition of the from higher order to lower order. That is the object to. Next coming to the need of the method. So that is what is the actual need. We'll see the later. So on the one. That is the next one is the description of our proposed method. So here the description is the method is to be comparing with the other method. So whatever the previous existing method. So what are the drawbacks of those methods? that is the compared with the proposed method. And what are the drawbacks present in the